All right, and now on to the cotangent. So again, in the cotangent, a couple different things. Remember, we're dealing with a new initial period. The period of the cotangent is just going to be pi divided by b, but the phase shift, the vertical translation is going to be the same. And then the asymptotes of the cotangent is actually the exact same as the cosecant function, which is something that we're going to kind of go back to and rely once we look at the initial period. So let's just go ahead and first thing I kind of notice about this problem is I do not really like this notation that it's in, right? Because I don't like the x not being in front. So what I'm going to do is I'm just going to rewrite this with the x in front. So I have a cotangent of negative x plus pi half, because that's a positive pi halves. And then I realize this is not in my form of b times x minus c. So I need to factor out that -1. So I'm going to rewrite this as a cotangent of -1 times x minus pi halves. So I can see that my phase shift, which again we can check with the link on Desmos, my phase shift now is going to be pi halves units to the right. So, which again, remember you can check all of these solutions here. Zoom up. You can check all these solutions here on this Desmos link. All right, so looking at this here, my period, we notice that my b is 1, so that's not going to change the period. Even though it's negative, that's just going to be the reflection. But let's just go with the period is going to be pi divided by b, which is 1, so or b is -1, but it's a positive distance, so a period is just pi. We do have a phase shift, though, which is going to be right pi halves. And then we also have a reflection inside of the function, so that's going to be reflecting the y-axis. Okay, so now let's go ahead and look at what this graph would be, just to kind of sketch the rough graph here. So the cotangent function is very similar to the tangent function. Actually, let's go ahead and look at what tangent looks like. Because for all the trigonometric functions, we use the reciprocal function to kind of like understand them. So just remember tangent, this is y equals tangent of x, had asymptotes at pi halves and at negative pi halves. And then the graph looks something like this, right? And again, these asymptotes occurred there, but when we look at the unit circle and we look at those coordinate points, right, we had 1, 0. Well, at pi halves, we're at 0, 1. So when you take the y over the x, you're undefined, and that's for the angle, pi halves. And we get the same thing down here when we're looking at, this would be 0, -1. And when you take the y over the x here, you're also undefined. So that was for 3 pi halves. Well, cotangent is obviously going to be the kind of like the exact opposite there, because now you're doing x over y. So when we go ahead and sketch the cotangent graph, which I'll use purple to make sure we're representing that, y is equal to cotangent of x, we can see that when I take my x over y for the angle 0, I actually have an asymptote. I have a vertical asymptote. So my vertical asymptote is now going to apply at 0. You can see at pi halves, I'm going to have 0 over 1, which is 0, so therefore I'm going to have an intercept here, so that's going to be pi halves. And then at pi, I'm going to again be undefined. So this is the initial period. Now, again, a lot of students will get tripped up because it doesn't look like sine, but you remember thinking about looking at that reciprocal relationship, that flipped relationship as that sine and cosecant had, that secant and cosine had. And you can see that this is like that mirrored image kind of feel of this. So so let's do it right there, and then I'll say put pi halves up here. So to do that mirrored image, it's actually going to be like this flipped image of this. And again, what we could do is we could choose points to go ahead and plot for that and to go and find the numbers, but that's exactly what the graph looks like. Now let's go and take a look at what's happening here. You can see this graph is being reflected about the y-axis as well as being shifted pi half units to the right. So if I needed to sketch this, and again, I'm just going to do a rough sketch here. Rough sketch of this graph. Well, the nice thing about doing a rough sketch is you can kind of pick your pick where the graph starts, right? Your reflection is obviously going to reflect about the y-axis. So you can take this graph and actually just reflect it. So now it's going to look like the tangent graph. The starting position here, rather than the graph having an asymptote at 0, it's now going to have an asymptote at pi halves. So I'm just going to make my new initial period. I don't know why I'm doing this as a 0. I'm just going to have my new initial period at pi halves. All right. And then obviously, if I added pi halves to pi, where this other asymptote is, then I would have another asymptote at 3 pi halves. And then halfway in between there would be where my intercept is, but I'm not really too confident as far as where it's going to go. But we do want to represent here the graph representing that reflection. And that is going to be my y equals cotangent of pi over 2 minus x. Okay. Now let's go ahead and talk about the asymptotes. So again, when we look at this initial function, you can see the asymptotes occur at 0 and then at pi, and that's the period. So the graph repeats from there. So therefore, there's going to be another asymptote at pi later. So when we're writing the equation of the asymptotes, we can write it as, the first asymptote occurs at x equals 0, and then plus pi, and then we're going to keep on adding pi, right? Plus pi, plus pi. So the way to represent repeated addition would just be saying represent that as multiplication. But how many times? Because we can actually, instead of addition, we can also do repeated subtraction. You could subtract pi because the next asymptote to the left would be at negative pi. So the way we represent that is by using a integer or using a variable n, which represents all positive and negative integers. So therefore, we just write this as x equals pi n, because we don't really need to write the 0 there. The range is nice because that's just going to be negative infinity to infinity. But the domain is going to be all real numbers in this case, except for where the asymptotes occur. Now, the problem in this example here is, let me actually write that in there. So the asymptote is x equals pi n. Now, for our equation, I'm actually going to have to delete this because I don't want it to get confused with the answer in the problem. You can see we have a couple operations here, right? Operations is we're actually shifting the graph pi half units to the right. Now, the important thing to notice is the negative actually doesn't impact where the asymptotes occur. And if you actually look at the graph and apply this reflection or don't apply this reflection, it obviously changes the shape of the graph, but it actually doesn't change where the asymptotes occur. So instead of my asymptote occurring at 0, it's now been shifted over pi halves, but then it's still added. The period never changed, so it's still plus pi n. So the actual equation of the asymptotes for this problem is going to be x equals pi halves plus pi n. So even though the parent function, the initial period is pi n, since we shifted the graph over pi halves, it's now going to start at pi halves plus pi n. And the reflection, again, does not impact it. But you could look at that. You could still solve this as with a negative, and you'd still get the same, answers. You get a different equation. If you solved it with the negative, then you get negative pi halves minus pi n. But those will still give you all the same solutions or asymptotes. All right, so let's go and take a look at this one. Again, remember, cotangent, just like tangent, is not going to have any amplitude. So that 3 is vertically stretching the graph. So when we sketch the graph, we're just going to try to make it a little bit skinnier than the regular cotangent graph. And then we obviously have a change in period with a b and then a vertical shift. So let's go ahead and write in our period. And that's just going to be pi divided by b, which is in this case is 2. We don't have a phase shift. We have a vertical translation. In this case, you can see that this graph is going to be up 2. All right. And you can also see that the graph is being vertically shifted up 1. So we're going to have this vertically shifted up 1. I'll take a break. Is it possible you come back? Thank you. Okay, so back into this. Vertical shift up 2. And then you can see there's no phase shift. We're just a change in period. So, and no reflections. So let's just go and take a look at the graph then and kind of see what we would have here. So we're going to still start at 0, but now instead of the period, as long as it's taking pi for the graph to repeat itself, it's now going to repeat itself within half a pi. So we're going to have an asymptote at half a pi and at 0. Half of that would be my intercept, which would be pi over 4. So the graph, and again, it's a skinny graph, right? So it's going to look something like that, because that's where that vertical stretch is. Now, as far as the range here, that's hard. So as far as the range here, we're going to do from negative infinity to infinity. As far as the equation for the asymptote, you can see that the asymptote is still going to start at 0, but instead of it being pi n, it's now pi halves n. So x is equal to pi halves n, because the period, you can see that the asymptote occurs every period n, unless there's a shift. Now, another way to look at this is basically say, well, all the asymptotes occur at, x equals pi n. Well, now we have this change of period, so we make that, so we just set 2x equal to pi n, and when you divide by 2, that's where you get x equals pi halves n. All right? So therefore, the domain in this case is going to be all real numbers such that x cannot equal pi halves n. All right? Now, in the same case, I kind of forgot to go over to this domain here, so let's go and do this. The domain here is going to be all real numbers such that x cannot equal pi halves plus pi n. All right, so now let's get on to the last two. Here I have y equals 1/4 cotangent of x plus pi. So again, this 1/4 is going to be horizontally or vertically compressing the graph, so it's going to just be a little bit scrunched up there. The period is not going to change. My period for my 1, so I'll just say my period is just going to be pi. However, I can also see that my graph here is being shifted. So I have a phase shift here. So my phase shift is, did I not do any ones? Okay, I did. Oh, and I forgot to shift this up. So this is +2, right? So we got to make sure that we shift the graph up 2 units. So my apologies. Got to make sure you shift that graph up 2. So just be careful with that. Actually, you know what? Yeah. So make sure you shift the graph up. I totally forgot. So my phase shift here is going to be pi units to the left. All right, so my phase shift is pi to the left, and then I have a vertical compression. So that's really it. So let's go and take a look at what this graph would be. Now, again, the graph is going to complete in a period, so we got that. Pi, but now you can see that the graph is actually being shifted pi units to the left. So if I was going to look at my initial period starts at 0. If it gets shifted over to the left, now that initial period is starting at negative pi. And if I add pi to negative pi, I would actually get 0. So I'll actually write this out. So therefore, the end of my initial period is at 0, which is the y-axis, right? Which is 0. And then so half of that would be at negative pi halves. And then here's going to be our vertical asymptote. And there's a vertical asymptote at 0 as well. And then this graph, remember, is horizontally compressed, so we're just going to kind of fatten this out a little bit and make it look just like that. So as far as finding the range, you can see that the asymptotes, the original parent graph started at 0 and then goes pi. Well, just because I shift this over pi units to the left, it's still actually going to have the same equation of the asymptotes because I'm just adding pi to it. So you can do what we did before as far as asymptotes go and set x plus pi equal to pi n. Well, now when you solve for x, you get x equals negative pi plus pi n. But what you notice is that's still going to give you the exact same asymptote equations as pi n. So you can just leave this as a simplified answer. There's nothing wrong with this answer. It's just not really simplified. But for different values of n, you're going to still get the same asymptotes. So I'm just going to use a simplified answer. So therefore my domain is all real numbers such that x cannot equal pi n. And then that's my domain. And then my range is going to be from negative infinity to infinity. Okay. All right, last but not least here, we have a negative on the outside. So we know that's going to be reflecting about the x-axis. So again, that's going to be a very similar transformation, just like the reflection on the y-axis as far as the shape of the graph. And then we have this x divided by 2. So again, we're just going to want to make sure we can rewrite that as 1/2 x. Okay? All right. So we can see that my b is 1/2, so I know I'm going to have a change in my period. So my period is going to be pi divided by 1/2, and that equals 2 pi. We have a reflection about the x-axis. And that's really it. I mean, the 1/2 is obviously going to be a horizontal stretch, as you can see, because originally my period was pi, and now my period is at 2 pi. So to go ahead and sketch this graph here, we are still starting at 0. There's still a vertical asymptote at 0. But instead of the graph repeating a period from 0 to pi, it's now going to repeat a period from 0 to 2 pi. So therefore, I know my intercept is going to be at pi. But since the graph is being reflected about the y-axis, like if you take this initial graph and then reflect it about the x-axis, you can see that it's going to take the shape of like the tangent graph. Okay? So now we can also take a look at our period. And hopefully you can kind of see that, or not the period, but the asymptotes. You can see that the asymptotes are going to be, 0 plus 2 pi n. But if you want to set your equation for x over 2 equals pi n, which is our original asymptote, then you'd still get the same answer when you multiply by 2 on both sides. So the asymptotes in this case is x equals 2 pi n. The range is still going to be negative infinity to infinity. And the domain is going to be all real numbers such that x cannot equal 2 pi n. And there you go, ladies and gentlemen. Now we are finished with graphing our reciprocal functions. The main important thing is what we've come to look at is these equations of the asymptotes. Remember that cotangent and secant have the same equation, whereas cotangent and secant have the same equation, whereas cotangent and cosecant have the same equation for asymptotes, as well as secant and tangent. So that's important. As far as our reciprocals, just remember when we're looking into graphing the secant and the cosecant functions, it's very helpful to know what the graphs for sine and cosine look like. And then also just remember that tangent and cotangent, they're kind of like in their own little world, right? But their period is going to be pi over b, not 2 pi over b like the rest of the trigonometric functions. And then also, last but not least, just just make sure you are careful with not including amplitude, because amplitude is only for the sine and cosine functions. But besides that, guys, that is basically it for our reciprocal functions. And I hope you helped you out in this regard. And now we're going to go ahead and wrap up the unit. Cheers.